Apologies. Thank you, engineer, for recording the session. So from normal practice, in Kenya, we use an Emax of 6%. We use an Emax in 6% in Kenya. So there's also a requirement that, or it's always ideal to choose the Emax that you're using based on region or location. For instance, in Kenya, we say that it's 6%. Why are we saying that it's good to choose the Emax based on the region or the country? Because of driver behavior. You find that in Kenya, all these drivers, they know, like they can feel the impact when they are driving through a curve. So if you adopt the same Emax, the driver will be just prepared mentally. I think it's just by instinct. They'll know that if I navigate a curve that's this tight, the road will be banking in this much, right? But now, if you fluctuate your Emax, let's say in some regions you're having an Emax of 8%, in some regions you're having an Emax of 4%, it will be a bit confusing, and actually your roads will be having a lot of black spots. Why? Because there is inconsistency, and also the driver behavior. Based on the driver behavior, most of them maybe will be new to that, and that will be actually a crash point. So we normally choose the Emax as well based on the region. So in Kenya, in normal practice, the super elevation should be 6%. And this 6%, remember, this is the one that's applied on the curves that have the minimum RD. So if your curve is too big, you don't really need to have an Emax of 6%, right? Also, when you check on this, it's saying that in urban areas, an upper limit of 4% should be used. Why? The reason why you use an upper limit of 4% in urban areas majorly is because in urban areas, of course, there's roadside development, right? So if you use an Emax of more than 4%, you're going to have a lot of challenges in terms of access. For instance, let's say this is our road right here. This is our road, right? We have a road like this. So you have some roadside development on this side and on this side. And you've decided to use an Emax of 6%. So if the road is banking in this direction, it means that for these people on this side, maybe the access will be a level access. But now for this one on this other side, because that section of the road has been elevated, you will be forced to provide ramps. And because it's an urban area, maybe you don't have that space for that provision of ramps. That's why when it comes to urban areas, 4% is quite enough. Actually, even lower than that is just okay. But then again, if you're dealing with urban areas, but it's on the super highways, 6% of course is accepted. Yeah. Then we also have the loops or the interchanges or the ramps. Now for those, because when you look at an interchange like a clover leaf, I think it's called that, the ones that there is a very rapid change in grade. For instance, you're having an interchange where you have a bridge, right? So we have something like an overpass right here. Then there's a road that goes below this bridge right here. Then you have a loop that comes from this overpass into the one on the underpass. So you find that you will be having a very rapid change in grade between these two. Someone who is driving at the top of the bridge going downwards into the underpass. Remember the clearance from the bottom, okay, the bottom top of the bridge to the FRL or the blacktop of the underpass road should be not less than, I think, 5.8 meters. So you can imagine you're driving from this top here, that's above maybe 6.5 meters, all the way down there. So you need an Emax of actually around 8%, not more than 8% though, but not less than 6% for you to navigate this ramp successfully, right? More so when the curve radius is a bit small. But now if that curve radius is wide, it means that you can just do that with maybe 6%, 4%. But if it's that tight, an Emax of 8% is permissible. But of course, you also need to discuss that with the engineer as it's illustrated in the design manual. Let me just clear this. That's okay. So right here, we're being told that, sorry. So either a low maximum rate of super elevation or no super elevation at all should be used within important intersections again, right? That makes sense. Then when you're having inadequate super elevation in your curves, it's going actually to cause some crashes, and you can be able to just relate that. You can be able to study that using the design manual. I don't know how to use these pens, so nice. Right. So when we go down there, we need to talk about the super elevation development. So the thing that you are watching, how is that video? The video that we got to watch, the 11-minute video, was basically about super elevation development. It was basically about super elevation development, right? Super elevation development, it's basically how your road is changing in terms of the inner edge, the inner and the outer edge, how that the elevation is changing so that the vehicle can be able to be to traverse through that particular bend. So we are told that super elevation development has two components. The first one is the tangent runout, and the second one is the super elevation runoff. So the tangent runout and the super elevation runoff forms the super elevation development. So I wish I can be able to get that. Is it this one really? Let me look for that video again so that we can be able to look at it. Do we have history? Let me just history. I believe this is the one. All right, amazing. So allow me to use this snippet here to explain the super elevation development. I'll take my pen right there. This is the one that I need. All right. So we've been told that super elevation, how can I remove this? Nice. So we've been told that super elevation development has two regions. The first region is the tangent runout, and the second region is the super elevation runoff, right? So the tangent runout is that movement from the normal crown all the way to the level crown. So look at this one is it's really plain. I think I need to take a snippet of this. Captain Felix, I don't know if you can be able to take a screenshot of this, then you send it to me so that I can use it to explain. I don't know if engineer is in the meeting.
Yeah. Let me do that and then I share. No problem.
Yeah, please. Via Telegram, kindly.
It's shared. It's shared. You can proceed.
Thank you. All right, amazing. So this is it. So I probably need to save it. Mhm. All right, apologies for that, but that's fine. So let me take my pen or my pencil. So super elevation development is into, we have two regions. We have the transient runout and the super elevation runoff. So when you look at this pictorial representation, this is your road. This is the center line. So the assumption for this is that the center line is a bit flat, but of course your center line cannot be flat based on your profile. I know you're yet to reach there, but the center line cannot be this flat. Then this is the inside edge of pavement, basically one side of your road, the right-hand side in this case, if you're traveling this direction, if this is your direction of travel. So this is the right-hand side of your road. And this one is the left-hand side of your road. So this is the outside edge of pavement, right? So this one lane, this is the other lane. So when you come down here, and where we have the A, B, C, D, this is the cross-section of your road, how it looks like. So at the first point, at the first region, that's region A, or the first, the location at A, we are at normal crossfall, what we call the normal crown. For this particular recording, they were saying that their normal crown is negative 2%. The normal crown depends actually on the location or on the region. In Kenya, we are having a normal crown of negative 2.5%. The reason why it's a negative is to allow water to flow from your road. So basically, water will be draining on the sides. Yeah. So now, when you move from region A to region B, actually this curve at this point is a curve that's it's something like this. So this entire region, we are having a straight at this point, then another straight, then we are having this a curve that's going in this direction, right? So it's a curve. So we are super elevating our road on this side. This side is moving upwards so that we are able to navigate from this point. We travel all the way to this far end at region H. So the first location, that's A to B is what we call the tangent runout. What's the tangent runout? Tangent runout is where, in this case now, the left pavement of your road is elevated from that negative 2.5% to a 0%, what we call the level crown, right? So the tangent runout is the transition from the normal crown all the way to the level crown. This is what we call the level crown. The level crown, the left-hand side of your pavement, has been able to elevate from negative 2.5% or whatever normal camber you're having to a 0% crown, to a level crown of 0%. So it means that the elevation of your center line of your road and the elevation of the outside edge of pavement is actually the same at that point, right? And when you use transitions in your road, this is where the transition starts. That's why it's called the TS point. What's the TS point? That's the tangent to spiral point. So it means that if you're going to have your super elevation, if you're having spirals in your road, just before that spiral, you should have the tangent runout section or region, right? Then from that point now onwards to the start of the curve, this is what we call the spiral to curve point. That's where the curve itself starts. That's where now you have the super elevation runoff, right? How does this occur? The super elevation runoff, the left side of your pavement will now be elevating from that particular 0%, the level crown, all the way to the Emax. Emax is the design super elevation that you're adopting. So if you're in Kenya and maybe this curve, it has a very small radius, so it means that the Emax will be 6. So it means that this elevation from 0% all the way to 6% will be at the super elevation runoff. But before we reach the super elevation runoff, there's a region in between that we call the reverse crown. That's section C. What's the reverse crown? Reverse crown is where the inside edge of pavement starts to rotate. Remember at this point, the inside edge of pavement, this side, is still at negative 2.5 or is still at normal camber, it's not rotating. When you come to the level crown, only one side is rotating, that's the left, right? It's raising to 0%, but the inside edge of pavement is still at the normal crown. But when you come to section C, that's the reverse crown, this point will be will start rotating, basically. So at this point, from point C to D, the inside edge of pavement and the outside edge of pavement are both rotating at the same pace, actually. So that by the time you're reaching point D, you are at Emax. So if your Emax was 4%, it means that at this point you'll be at -4, but at this point you'll be at +4%. That's basically it. So you've been able to transition from the normal crown all the way to full super elevation. And at the full super elevation, that's where your curve starts. That's where we have the spiral to curve, right? Now, your road now will transition with that full super, full super from that point all the way to the end of the curve where we have the CS. The CS is the curve to spiral. So now that's where we are having our spiral out. Then now at the spiral out, it's more of a backflow, like we're moving backwards from this point going this way. So we are now transitioning back from the full super where our road now is slanting at this position, but we want to go back to the normal camber or the normal crown in the next tangent that you're having. So the road will transition, both the inside edge of pavement and the outside edge of pavement will be transitioning at the same rate, moving downwards, all the way to point F where we'll be having the reverse crown. Now at the reverse crown, the outside or the inside edge of pavement will no longer be rotating, but the outside edge of pavement will now be rotating all the way to the level crown first, where we are having a 0% grade. Then from that 0% all the way to whatever normal crossfall you end, which is -2.5% in our case. So again, this is the tangent runout, which is actually the same. The tangent runout distance is the same as the distance from the level crown all the way to the reverse crown. Why? Because you find that the reverse crown is normally where the inside, okay, let me use this one as an example, where the inside edge of pavement and the outside edge of pavement are opposite. For instance, let's say this is -2.5%, this one should be +2.5%. Like it's basically the normal crossfall, but now in the opposite. Yeah, I hope you get that. So you find that if the distance now for you to move from -2.5% or whatever normal camber you have to 0%, then from 0% to the same normal camber in the positive direction should be the same. That's why the distance from this to this, A to B, is the same as the distance from B to C. That's basically what the illustrator of that short video was trying to show us, and I believe you've gotten something from that. Allow me to proceed back to the design manual. So on the design manual, basically this is the same thing. So on this representation, it's the same. At this point, this is where we are at our normal crown, where we are having -2.5, -2.5. Then when you move, the next stage is the level crown, where we are having a 0% on one side of our pavement. Then we are going to reverse crown. You can see this is slanting in one direction. 2.5%, -2.5%. Then we go, if your Emax is 4%, this is where it will end. If your Emax is 6%, this is how your road pavement will look like. So that's basically it. Then we have what you call the super elevation rates for different design speed. So when you check the RDM road design manual, we have this type of a table where we have the correlation between the super elevation rate, the horizontal radius, and the design speed. Reading this is quite easy, because now let's say you have a design speed of 40 and your curve radius is 100. So this one will tell you what super elevation will be your Emax, because you'll just go to 100, then you move to this point, you see it's around 4 point something thereabout. So this is what we used to use, or what the engineers used to use before the softwares. But now the good thing is the software, the Civil 3D software, is able to pick this information from whatever design criteria file is inserted, or Yeah, basically. So you find that when you calculate the super elevation using the software, you're not going to assign the Emacs. The software will just pick based on the criteria files that you choose. Such that if you're having a section that you're having a design speed of 70, and for that section, your curve radius is 300. So the software will just correlate horizontal radius is 300. It goes all the way to a design of 70. You find that your Emacs will be around 5.2. So for that particular curve, it will assign an Emacs of 5.2. So picture this. When you try and look at this, you find that the more or the tighter the curve radius, the smaller the curve radius, the higher the super elevation value. And you find that others cannot be applicable. For instance, this where you're having the dots. It's telling you that you are in a danger zone. For instance, you're having a design speed of 70. Look at this. Then your radius is 500. You find that the Emax is around 3 point something thereabout. But now, if the radius comes to something like 200, the Emax increases all the way to danger zone, 7% thereabout. So that shows you the correlationship or the relationship between the super elevation rate and the horizontal radius and the speed as well. So the tangent runout is basically what we've talked about. It's that movement of one or the outside edge of pavement from negative to whatever normal camber you're having to a level crown. And we've been able to talk about the TS, the SC, the CS. Basically, that's what this is talking about. The super elevation runoff, basically from the level crown all the way to Emax, and at the same time from the Emax all the way to level crown when you're transitioning back. There's a formula that you can use to determine the L naught. L naught is the super elevation runoff, right? And you're told that the length of runoff, which is right here, is the spiral length with the tangent to spiral point. Look at this. We said that if you're having spirals, this is where your spiral starts. That's why we call it the tangent to spiral. And this is where the spiral ends. That's why we call it the spiral to curve. That's the entire region where the super elevation runoff is modeled. So it's safe to say that whatever spiral length that you're using, either the spiral in and the spiral out, that same length is the one that will be used for super elevation runoff, right? And we're told that a simple practical rule is that it must not be less than the distance traveled in 2 seconds at the design speed. So if you have your design speed, you can be able to determine the distance that someone can use to travel in 2 seconds based on that design speed. That should be your minimum value of the L naught. And the good thing is that the software has been able to give us some values. And if you want to check if your super elevation will be okay, you get to see the spirals that you use. You compare it to the design speed, then you know. So this is basically talking about the transition curves. I believe we've been able to talk about this when we're doing the horizontal alignment. So basically the transition curve, that's where the super elevation runoff will be modeled. It's really important, but there are some instances in which the transition curves are not really required. For instance, where is that? We have it here. Not all cycler curves require spiral transitions, where we have large horizontal radius, of course. And again, if you're having very large horizontal radius curves, you don't really need super elevation as well. Where the operating speed is less than 70 km, there's that also. You can be able to read through this, but allow me now to go to the software. But before I go to the software, this is another pictorial representation of super elevation. You can see at this point you are at normal ground, where we are having a slope, a negative slope in both directions. This is more of a 3D view. Then when you come at this point, this is where you have the level crown, where this one has been able to rise up to 0%, and the left is at a negative crossfall. The next one, I believe this is the start of the curve. So this is where we are at Emax. So we ought to have a reverse crown at a point like this, where this line is now straight. Like we don't have this flatness at this point. So we have a reverse crown at this point. Then we are having Emax at the start of the curve. Now at the end of the curve, that's where we are still at full super. Then we'll transition back to a region in between here, which is the reverse crown, back to the level crown, and back to the normal crown. So when you go through the design manual, all right, there are some pictorial representation as well of how super elevation can be able to look like, depending on whatever entities you are having in your design. For instance, for this is where you're having a straight, then into a circular curve directly without a transition or a spiral. So this is how the super elevation will look like. For this one, this way you're having a circular curve, a spiral, another spiral, another curve. So this is how the super elevation will look like. For this one, you're having a straight, a spiral, a curve. So if you got to use this method in designing your horizontal alignment, this is how your super elevation will look like. So you can be able to go through that and look at that. But allow me now to go straight to the software so that we can be able to just try and calculate the super elevation unless someone has a question for me before I proceed. So I take some questions as I open my Civil 3D. I can see we are having a question in the chat box. Assuming we have a divided median row, does the super elevation graph still remain the same? Yeah, basically it will remain the same. Base now, I think it will, you will choose where you want your pivot to be. Is it the median or is it the edge of the pavement? But then again, you find that when you're having a divided median, the curves will still be moving in the same direction, right? So I think those graphs should be the same as well. And I can see, yeah, that's the same pictorial. That's okay. So majorly, when you're dealing with dual carriageways, you can choose to have your pivot to be at the edge of the curve or at the edge of the road. But as well, you can have it at the median unless you're having a median drain or something. So that now that can be able to limit you. So this, I hope I'm still sharing my screen. Yes, I am. So allow me to open a drawing that I'm going to use to move them to screen elevation. So should be on downloads. All right. So this is the design that we're going to use for today's session or for the super elevation modeling. Allow me to turn off the surface. Okay, that's that. So we can be able to work with this as it is. That's okay. I like to turn these ones off as well. This one can work. So we can be able to use this one as is. So how then can you calculate your super elevation? So what you do is you just click on your horizontal alignment, then the contextual ribbon will pop up. We've been able to explore the alignment properties, the geometry editor. Yes, we also did this. So now the next one is the super elevation. So you just click on that drop down. Then we are having some more tools right there. The first one is to calculate or edit super elevation. So if you're doing it for the first time, that's where you use the calculate or edit. Then if you've done it already, you go to the view tabular editor. If you want to make any edits, same as creating a super elevation view. For our case, you're going to calculate the super elevation. So I'll click on that. Then it will ask me if I want to calculate it or open the super elevation curve manager. Of course, we want to calculate the super elevation now. Then after doing that, we'll be having this super elevation wizard right here. So we need to choose our roadway type. We are having the undivided crown and the undivided plano. So the first thing is the undivided or divided. The divided, of course, is the one that has a median. But when you talk about the undivided, is the one that we don't really have a median. So crown roads or planar roads. Our road is going to be a crown road where water can be able to just flow on the outside of the center line. These planar roads are majorly estate roads or township roads. Why? Because maybe you don't really have space for drains on the sides and the sort. That's why you slant your road in one direction so that you only provide a drain in one side. So I've seen a lot of planar roads in towns or in regions where we don't have the luxury of space, but crown roads is what we normally use on most of our roads. So we'll choose the crown road. What's our pivot method? This is so you can be able to choose it. Is it the center line baseline? Is it the inside of the curve or the outside? Whatever. For our case, it will be the center line. So it's the center baseline. Of course, our road doesn't have a median. So now we can be able to go to the lanes. This is where you define your lane because remember, super elevation is based on, actually it's based on elevation. It's going to change the elevation of your road. So it means that if you're having a wider lane width or a carriage width, the elevation at the center and the elevation at the end or the outer or inner edge of pavement is going to be impacted by the length of the carriage width. That's why we are defining our lane width. For our case, it's going to be a 3.5 meter lane. But first, before I define this, if your lane is symmetrical, you'll have to check this symmetric roadway. If it's not, you can uncheck it. But I've not seen a road where we are having different lane width, unless you're having an acceleration or deceleration lanes, additional lanes that is. But for our case, it's symmetric. So the number of lanes on the right, of course, you're having one lane. On the left as well, you're having one lane. So I'll just check off this one. This one remains as one. Then for the lane width, it will be 3.5. We'll be designing a lane width of 3.5 meter. The normal lane slope, you can see the one inbuilt in the software is 2%, the default. I think because for the Americans, the hashtag it is 2%. Based on that video that we got to watch again, they are saying 2%, but in Kenya it's 2.5%. I think, is it in Ghana that's 3%? I'm not sure, but you can be able to check your local design standards or your local road design manuals. Then you get the normal lane slope. That's basically the crossfall. Then we go to the next. This is where we have the shoulder control. We don't really have, or we don't really calculate super elevation for the shoulders. As you can see from our road design manual, under the shoulder, it was remaining at 4. So we'll get to uncheck that. Then the next one is the attainment criteria. The attainment criteria is basically the files or the files, yeah, it's the files that you are instructing the software to use when determining the Emacs or when modeling the super elevation, right? You can choose it, the criteria file, you can choose it from that particular point where you're having these criteria files. So for our case, you're going, we have the metric. So we have the 2011 metric, the 2018. Can be able to explore the two, but let me go with the 2018 design manual, then we see what that happens. Then of course the Emacs, you need to choose the Emacs as well. You're having 4%, 6%. So depending on your region, assign the Emacs. But remember, this Emacs, it doesn't mean that the curves are going to have an Emacs of 6%, all of them, no. So you can be able to attain to have it at 6%. Transition length table. So we have two tables for transition length. The same table like the one that we saw in the design manual. So the AASHTO standards has inbuilt criteria files that the software can be able to pick. So the software will go to this criteria file and choose between the 2 lane and the 4 lane. Remember, our road is only 2 lanes, but now we'll just assign it for the 2 lane for that case. Then the attainment method again is the AASHTO. It will pick based on what you choose there. Then you have the transition formula for super elevation runoff. The first one is asking us percentage on tangent for tangent to curve. Tangent to curve means we don't have a spiral. So your road is you're just having a tangent. Oh, cannot be able to draw on that. So you're just having a tangent, then another tangent and a curve like that. We don't have a spiral. So if that's the case, the attainment criteria is 2/3. When you do this one, 66.67, I think it's 2/3, meaning 2/3 of the super elevation will be modeled on the tangent. So that by the time you're reaching the start of curve, okay, now at this point it will be tangent to curve, TC. By the time you're having the TC, you only need a third into the curve for you to attain full super elevation or the Emacs. That's basically the attainment criteria. But now, if you're having spirals, it means that the entire super elevation runoff will be modeled on the spiral. That's why it's 100%. So you can be able to remove this as well. So that's that. The next thing is curve smoothing. We don't really need that, but we need to automatically resolve any overlap that we might have. Then you get to finish. And when you finish, you just give the software a minute to do the computations. And just like that, you can be able to see that you already have a super elevation table. So when you look at this table, this is what we have. So basically, under each curve, you have super elevation. Each of these curves, unless the radius is really, really, really big. But for this, you can be able to see that you are having a curve 1, you're having a curve 2. So you can be able to review the super elevation data from this one, or you can be able also to export it to an Excel file so that you can be able to review it well. So I'm going to talk about these tools right here quickly. So the first one, of course, is to collapse. The second one, I think, is to expand. So just collapsing and expanding this table. When you go to the next one, where you're having the addition sign, this is for adding a super elevation critical section. What do I mean by that? Let's say you've assessed your super elevation and you find that for some reason you're missing a section. And just before I go to these tools right here, let us look at this. You can see at this point that already you have the super elevation labels. So this is what we call the super elevation labels. So at this point, we are at normal crown, negative 2.5, 2.5%. Then at this next point, we are at level crown, where one side of the road is at 0%. Then we are at reverse crown, then we are at full super elevation. That's where the curve starts, as you can see from the alignment style that engineer used. The alignment style here is yellow for the curve, and that's where we are having the full super. So we will transition with the full super up to the end of the curve. Then now we transition back from the full super all the way to the normal crown, as you can see. Then for the next curve, we'll start the same procedure again from the normal crown all the way to full super back to normal crown, just like that. So that's that. So now allow me to talk about these tools right here. So for adding a critical point, let's say you missed a point.
Engineer, one second.
Yes.
I have a small doubt. Let's zoom in here. Yes. In image, you have shared image.
Yes.
Super elevation image.
Oh, you want us to go to the image?
Yes. Yes. From here, at TS, it has 0% and normal curve.
Yes.
In drawing, it will reflect like that only.
It should actually. Where you're having your spirals, it should. Where are your spirals? So your spirals are in magenta, right?
Yes, TS to SC is spiral.
So probably what you need to check is the length of the spiral that you have.
Okay.
Because the software has pushed the level crown a little bit behind. Maybe this you need to check the length of the spirals that you're having and correlate it to the design speed and check the design manual on the tables for the required transitions. Check if those tally. If they do tally, you should be having the same representation where the level crown should be at the start of the spiral. Then the super elevation runoff, which is from this level crown all the way to the Emax, should be on the spiral. So kindly check on that. And thank you for picking on that actually. That's really important. That's how you check and you make sure that this one is okay, your super elevation is okay. So allow me to proceed. I'll click on this, then I'll go back to super elevation. But now for this case, because we've done the calculation, we'll choose the edit. So we'll have the edit. Yeah, so this is the table that we'll be having. Tabular editor. This is what we'll be having. So the cross sign here is for removing a region. For instance, you don't want a region, you can be able to click on it, then you can remove it, right? Just like that. And that region will be removed. So of course the software will take some time to do its computation. Then I just want to undo that by showing you the next tool. You have a tool for redo and undo. I probably should not have done that because I can see that the software is taking too long to compute it again. But that's fine. I can be able to talk about the next tools. So that's for deleting a region. So this one, the next one, we have two tools right here. One is for exporting the super elevation data to an Excel file. You can be able to export from the software to an Excel file. The other one is for importing. So you can be able to do or generate your super elevation values based on manual calculations, which also will depend on, so it means that you need to know the curve radius for all your curves, what else, the design speed at that particular curve. Then you can be able to calculate the super elevation that is required for that curve. Then you assign it, based on that, calculate the super elevation runoff L naught. Then after getting the L naught, you get the tangent runout length. Then now you can be able to distribute these regions from the level crown or the normal crown all the way to the full super. Then you can be able to generate an Excel of that. Then you can be able to import it. So if you can be able to do that, you can be able to use the import. So this is the import. So you can import a super elevation data from a file, the file that you generate. For this one, you can be able to export. This one is for undo, and the other one is for redo. Then the last one is for clearing everything up at this point, right? So I like to export this data to an Excel file so that you can be able to look at it closely. So I just take it to downloads, then I save it. It will go as a CSV file. So it means also if you're calculating a super elevation from scratch, you need to do it as a CSV file for you to be able to import it to Civil 3D. So let's go to this. Let me just open this. Yes, so this is how your super elevation data will look like. Let me just get to expand all of these. Yes, so that's what we have. So when you look at this, the first one is the region, not the region per se, or the curve. So this is the first curve, the number one. Number two is the second curve, like that, like that. The second one is the station, from where to where. So the software is able to track it, to track all the stations. For instance, at this point, we were at normal crown from chain 00, where our tangent starts, all the way to 154.4, where the level crown starts. So I think I got to, there's that section that I removed that was at the beginning of normal crown. Or sorry, at the end of normal crown. Remember, there's a section that I got to delete. So the normal procedure for this is beginning of alignment, which is we normally like to begin at a straight. So we'll have beginning of alignment, then you'll go to the end of normal crown. End of normal crown. Then from end of normal crown all the way to the level crown, that's the tangent runout. From the level crown to reverse crown, then to full super elevation, that's the super elevation runoff. Then from beginning of full super or beginning or begin full super all the way to end full super, this is where the curve itself is. Then after the curve, you transition backwards from end full super all the way to level crown, that's the super elevation runoff on the spiral. Then from level crown to beginning of normal crown, that's the tangent runout again. Then you start the same process. Beginning of normal crown to end of normal crown, that's the tangent, that's the straight section, that's the tangent section. But from normal crown to level crown, tangent runout, same. So it will be a repetition of the same thing again and again. So that's the description. Then the next one is smoothing. We say that we don't have smoothing. That's why these values are all 0. Then we have the left outside shoulder. Please can kindly mute. So we have the left outside shoulder. We don't have super elevation on the shoulders. That's why they are all 0. Left outside lane. That's our lane on the left, right? So you can be able to see the values of super elevation. But when you look at this super elevation, you can see that almost all the Emacs are around 6%. So it means that something is quite off. So you need also, you can be able to recalculate on your side and probably assign the design criteria of 2011, because I'm not sure about this, why it's picking 6%. And yet when you check the curve radius for this first curve, it's not that tight. It should not be having an Emacs of 6%. So you can explore and check what the issue might be. But this is the super elevation basically. Of course, at the beginning of alignment, it's negative 2.5, negative 2.5. So we are relating the left outside lane, this one, and the right outside lane, right? Because we don't have an inside lane, we don't have a shoulder, we don't have a right outside shoulder, right? So we are relating this to this, negative 2.5, negative 2.5. When you go to the level crown, negative 2.5, the other side should be 0, right? So you can be able to just relate this. When you go to the reverse crown, this is negative 2.5, this is positive. Then at full super, for some reason, it picked 6%. So it means that the software has not been able to use the criteria files that we've assigned. So maybe you check on that particular criteria file, or you can also be able to change it to the 2011, then you see what happens. But basically this is that. So the only thing that you can be able to review at this point is the stations, and of course the regions, because all of these are 0. But now the thing is, if you're going to generate the super elevation file from scratch, it should be in this format. You need to have this table. you need to have this table, you need to have this table. It's quite tedious to do it. The software can just be able to do it, then you can do some bit of adjustments here and there using Superelevation editor. So you can be able to model your Superelevation, you see what you have. Then of course you have your alignment labels to show the Superelevation how it looks like. Then now you can be able to just critique or evaluate what you're having based on your horizontal alignment. I believe that marks the end of my presentation today, and I will take the one question, then I can invite Engineer Felix to take over.
Hello. Hello.
Hello?
Yes, I have a
Hello?
question.
Yes.
Whenever we are going from highway to bridge to go the other side, so we have like eight type of interchanges. Did you what I want to say? If we go to any from highway,
I'm not sure if I
hello.
got your question. Yes, yes, yes.
Yeah. Whenever we are going from any highway to towards city, so there is a exit. So it is from on the top of the highway. So we are taking like a round. There is a round curve. There is super elevation also there. So that is also same calculations we are doing for that super elevation.
I don't know if I got your question right, but I believe you're talking about the loops at interchanges. Is that right?
Yeah, the loops. Yeah, that is what I want to say.
Yes. So for the loops, I remember saying that for the loops, the super elevation can be up to 8%. But so if the loop radius is a bit small, because also you see that you're having a very rapid change in grade.
Yeah, it's very rapid changing and elevation also very from you can say from 0 to it's going to be a 12 meter or maybe 30 meter, something like that.
No, that is too much. Because you're talking about the clearance of the bridge. For
Yes,
instance, if
that
you
is
have,
what. Yes.
let me get to reshare my screen. Then I probably need to find a place where I can go. So I'll go back to the design manual. So let me just get to draw. Let's say we are having an overpass at this point. This is the road that goes that's on the top, right? Then we have our bridge at this point. So we have a bridge, meaning that we have an underpass at this point. We have another road at this point. This is basically more of a clover leaf. So we are having a loop for someone who is traveling on this top side, but he wants to come to this point.
Yeah, this is what I think.
Yeah, so this is what you're talking about, right?
Yes.
Yeah, that's okay. So you find that the minimum clearance between the bottom of this or the top bottom of this bridge to the final road level for a road here should be around 5.8, if I'm not wrong. Kindly confirm based on your design manual.
This is the correct height.
Yes, it's around 5.8 meters. But this one now, you've not added the thickness of that particular of your deck. So it means that this distance can come to almost around 6.2 thereabout to 6.5 maybe, right? So it means that if someone is to move from this level at this point and you want to come to this point here, the level difference will be 6.5. And it gets worse if this profile of this road is uphill. If the profile of this road the one that's on the top is upping like this, it's a rising gradient, it will be worse. So this distance can move all the way up to maybe 8 meters. So if
Okay.
you want to move from that particular 8 meter to a 0 meter down here, it means that, and maybe this length is a bit small, the super elevation should be quite high, around 8%, for you to be able to navigate that loop quite fast and safely.
Okay.
Yeah.
Thank
So,
you.
all right, you're welcome. I now invite Captain Felix to take us over to the next session.
Thank you so much, Engineer, for that insightful session. Kindly confirm if I'm audible enough.
Yes, you are audible.
Okay, thank you, Rashid. Thank you. I see that we are well past the time that we had intended to start on another session, right? We had earlier on begun by describing, the typical workflow that you will need to stick to when we are designing our roads, right? So the large chunk of it, which is associated with the horizontal alignment, has been covered, and we mark the end of it by doing what Captain has just demonstrated, which is a super elevation calculation, right? So the horizontal bit of it is through, and that is going to be part of the deliverables. Now, the second part, after we are through now with the design of the horizontal alignment, we typically usually head over to vertical alignment, okay? And that's what we wanted to cover. And just like is standard with our demonstration, we like to ground ourselves in the manuals. And I will take this opportunity maybe to, discuss it. We will revisit the manuals, know the parameters that we will stick to once we get to our softwares. Of course, before we start designing our objects. Vertical alignment is actually quite easier than even horizontal alignment, because the entities that we'll be dealing with are quite few, right? Just basically gradients and curves, right? So what am I talking about? Let's get into the manual so that we can get a deep understanding of the same. Now, if time doesn't allow us, we will simply push the software bit to the next lesson, where we will get to handle, of course, the actual design of the profile, together with the creation of data bands, which is, we like to equate it to, or, it's equivalent to, or the first part of the plan and production, okay? If you are going to produce your drawings, it's very, very important that you have your what we call plan and profile. And in your profile, we need descriptions of what it is that you have in your drawing. So that's where the data bands come in, and we will take a whole session to discuss it. But more on that later. So let us proceed to, have a quick discussion on, the vertical alignment and the basics of what we need to understand before we get into the actual design process, okay? So I will share my screen and we will get straight to the RDM 1.3, which is basically, where is it? There we go. Which is basically the guide that we abide by within the Kenyan region or Kenyan country. But remember, this manual, most of it borrow heavily. I like to, I know it borrows heavily from AASHTO, and of course it has been configured to fit into the local standards. So what do we mean by vertical alignment, right? I know we fully understand what horizontal alignment is, but what is vertical alignment? So vertical alignment is basically, the longitudinal profile of the road. And just like I mentioned, it simply consists of straight grades, which are the tangents, could be uphill or could be downhill, right? Sorry, could be uphill, right? These are straights, or could be downhill, right? So uphill are defined by the positive gradients, and downhill by negative gradients. So that's the first thing that you might need to understand, right? That is the grade. And the other component, of course, is the vertical curves, right? Basically the crest curve and the sag curve. I know you guys are engineers and you already understand what the difference is. You know, crest curve is more of a convex shape, and sag curve a concave, right? And those curves provide, of course, smooth transition between the two gradients that we discussed, all right? And we do have, circular curves, and we also have parabolic curves. Now you will realize that in our vertical alignment, we basically focus, or not even focus, we basically use the parabolic curves. And that there's a reason for it, right? It's because the parabolic curves provides, or simply gives us, a constant rate of change, what we have at this point, constant rate of change of curvature. Unlike, the circular curve doesn't provide that, right? It has a variable rate of change, and because of that, it's avoided due to the discomfort, right? And the abrupt changes. So make no mistake, we are not going to be using any circular curves like what we've been using in our horizontal alignment, but we will use what we call parabola or parabolic curves. Parabolic curves, of course, they are derived, or their equation are quadratic, right, in nature. So definitely it's, the y component is going to be dependent on the x component, right, as defined by that equation we will see shortly. And, those two aspects of vertical alignment, basically the vertical curvature and the gradient, they are parameters, or, aspects that govern, how we get to use them, right? So for the vertical curvature, it's governed by sight distance criteria. That is both the sag and the crest curve, right? We use the sight distance criteria to get their parameters. Now, the gradient is also informed by vehicle performance, right? And level of service, right? We don't use sight distance when it comes to the straights because, of course, it's a linear path, right, of sight. So whatever distance it's going to be, you're going to be able to see the end of it. Of course, this is on assumption that, horizontal alignment doesn't come into play, and you don't have any curves to the left or to the right, right? So the gradient are going to be limited by the vehicle performance and the level of service, right? Now, let's see the basics of the vertical curve formula. We'll start with the curves, right? I know this already looks familiar. This is essentially the straight that we've been discussing, and the other straight, defined by their grades. You can see the first grade defined by G1, which is grade 1, and the other grade defined by G2. Remember the gradient 2. And joining them is a parabolic curve, okay? Parabolic curve of length, of course, L. And yeah, it's basically a chord. And of course, the difference between, that point of vertical curvature, this is beginning of vertical curvature. EVC is basically end of vertical curvature, right? So from the definition of terms, same thing when it comes to our sag curves, and simply just check this. I know we share